All right, in this video segment, we're going to look at doing some titration calculations. Again, we already talked about finding the equivalence point. That's actually going to be the first step that we do for this problem. It says 20 milliliter sample of 0.200 molar HBr solutions titrated with 0.200 molar NaOH solution. Calculate the pH at these following volume additions. So, first thing I would do is figure out, well, what is the equivalence point? Because I want to know where am I in relation to the equivalence point with these volume additions. And so again, I can use this equation, the molarity of the acid, or the molarity of the H plus concentration if it's polyprotic, times the volume of the acid equals the molarity of the base times the volume of the base. And so plugging in what they gave me, I have 0.200 m times 20. And you can actually kind of already see if the base and the acid have the same exact concentration, and it's a 1-to-1 H plus to hydroxide concentration. You can kind of tell how this is going to come out, but the volume of the base is going to be 20 milliliters. Okay, so the equivalence point will be once I've added 20 milliliters of the sodium hydroxide. That's when I'll have completely neutralized the acid. Now, since these are both strong, again, the pH at that equivalence point will be 7. If I had a weak acid and a strong base, as we talked about with the salts hydrolysis and the interactions with the leftover cation, anion in solution, a weak acid with a strong base would give us a pH in the basic range greater than 7. If I have a strong acid and a weak base, then at that equivalence point I would end up with a pH of less than 7, because the acid component would, the conjugate base would be giving us an acidic solution by interacting with hydroxides, and so forth and so on. So anyway, there's our equivalence point. So when I'm adding 15 milliliters, I'm not yet at the equivalence point. So when I do part A, then I want to think about what is the reaction. So I have the again, the HBr, so want to think about, so I have 0.200 liters, right? If I convert that to liters, and times the molarity, which is in moles per liter, that means that I have 0.00400 moles of HBr present in my flask or in my beaker. Okay, so that's going to be my starting amount for my acid. Again, it's going to be the H plus that's reacting. The Br is going to be a spectator, so I'm not going to write that down, but I have 0.00400 moles. So we want to do these stoichiometry in terms of moles because we're dealing with adding volume to our system, and so that's going to change the concentration as we increase volume. So we want to make sure that we factor the volume change in at the end. The H plus is going to be reacting with the hydroxide from the base, and again, if I'm adding, let's see, for A, they said I'm adding 0.2 molar, it's moles per liter, times, I'm adding 15 milliliters, so that's going to be 0.015 liters, so 0.2 times 0.015, so this is 0.0030, and that's moles of hydroxide that has been added. So I have 0.00300 moles, and then this is forming water. And again, there'll be those anion and cation left over that are spectators, and we don't really care about them. So this then, all of my hydroxide is going to get used up. That's the limiting reactant if we're titrating that in. So all of that gets used up. And I know that I'm below the equivalence point. That's also how I know that there's no excess of the hydroxide. And that means then that I am forming this many moles of water, and I don't really care about that too much, but I have 0.0010 moles of H plus. I have 0 moles of hydroxide because that was all completely neutralized, what was added. And so when I'm looking for the pH of the system now, then I know the pH is the H plus concentration. So be careful though, well, the pH is the negative log, you know what I'm saying. Well, be careful though, because this is moles of H plus, right, that's left over in the flask unreacted. But now, since I had 20 milliliters of acid to begin with and 15 milliliters of base was added, I now have 35 milliliters of volume total. And so I have to factor that in when I'm looking at my concentration of H plus to find the pH. So 0.001 divided by 0.035. So my concentration of H plus is 0.0286 molar. And so the pH of that, so the negative log of that, is 1.5. Get on the screen here, 1.54. Let's see here, should we be keeping 3 significant figures? Yeah, so 1.544 technically is what I should have for my pH for that. So when I go to do the other parts of this problem, like for this one, so at 20 milliliters, well, again, since this is a strong acid and a strong base, at 20 milliliters, we figured out that is the equivalence point. So that's going to be pH of 7. And again, if you look back at the numbers that we did here, well, this would be 0.0040 moles of hydroxide that was added. So that would be exactly the right amount of both of these to neutralize each other. We have water, we don't have any excess of H plus or hydroxide, and that's why we'd end up with a pH of 7 for part B. Or sorry, this is part C actually. This is from one of your homework problems. Ooh, I'm doing your homework for you. And then for E, so let's take a look at this. If I've got more than the equivalence point. So I know that 20 milliliters out of the 35, that's been neutralized, right? So once I've added 20 milliliters of sodium hydroxide, that's all been neutralized. So that means I have 15 milliliters of extra sodium hydroxide that has now been added into my flask that we're going to notice the pH for. So I've got a total volume of, let's see, if I've added 35 milliliters, I had 20 milliliters of acid to begin with. So these are just this initial acid concentrate or volume. This is the amount of base that was added. I've got 55 milliliters total volume. Total V. All right, so that means then when I'm figuring out what is the new pH, well, I've got 15 milliliters of sodium hydroxide unreacted, because again, we're 15 milliliters past the equivalence point. So with 0.2 molar sodium hydroxide, again, the 15 milliliters technically needs to be divided by 1,000, right, because we want to use it with the molarity, you have to have it in liters. So this is 0.00300, that's moles of sodium hydroxide. All right, and so it's this number of moles of, again, that's the amount of hydroxide, 0.0030 moles of hydroxide divided by the 0.055 liters. Again, we need to get this into molarity before we can use it, divided by 0.055. Okay, so my concentration, now again, paying attention, this is the base, this is concentration of hydroxide. When I do the negative log of this, that gives me the pOH. So the pOH equals 1.263, so that would mean the pH 14 minus that number is 12.737. Okay, and that makes sense because we're past the equivalence point, so when it's exactly neutralized all the acid that was there, we had a pH of 7. Now we've got extra hydroxide that's there. The acid is no longer there, contributing H pluses. So that's why we have this pH in the basic range. And you know, the more hydroxide you keep adding, the more the pH is going to increase. And there you go.